that maize yields, essentially since the 1930s, have increased at really close to a linear rate of nearly 2 bushels per acre per year. So about 1.8 bushels per acre per year. It's actually this increase is pretty remarkable, because if you go back before the 1930s, you go like 100 years before that in the 1800s and so forth, yields had really been essentially flat before that point. Farmers planted open pollinated varieties, and while there were a lot of efforts towards breeding and so forth, they didn't really get much of an increase in yields. And so it was in the early 1900s that hybrid vigor was discovered, and they were able to commercialize that into hybrid varieties, and then farmers took that up pretty quickly, beginning in the 1930s. And then basically since then, you've had this upward trend in yields. And so that fact is pretty widely known if you've looked into this area. But somewhat lesser known is, or at least to my mind is lesser known, is at the same time that yields were increasing so much, is you had this other input change going on, and that is in planting rates. So when I say planting rates, and I'll distinguish this in a bit, but planting rates, by that I mean corn plants per acre. Some would call it the plant population, but it's essentially the number of plants that you have standing at the end of the growing season on an acre of land. And so during the same time that yields have been, making this substantial increase, you've also had this huge increase in planting rates. And so if you go back to the 1960s, for example, you had farmers planting about 14,000 plants per acre based on USDA data. And now in modern times, today, it's all the way up to 30,000 plants per acre. So more than doubling just since the 1960s. And so it's this really, this interesting mechanism where, there's different ways you could get more yield in corn production. You could have more yield where you basically plant the same number of plants, but the yield per plant keeps growing and growing and getting bigger and bigger. Or you can basically pack more and more plants in the same amount of surface area, but you don't sacrifice too much in yield, and that's where you get more yield. And it's really been the latter mechanism that you've had an increase in yields in corn. And so, yeah, but I mean, what this says is that, today farmers, it's just, they've been packing more and more plants, same surface area. So you go back 40, 50 years, it's actually the yield per plant is actually not much different than it was several decades ago. It's a little bit higher than it was, but not much different. So given that you have this this relationship between planting rates and yields, combine that with the fact that when you look into the purchase choice that farmers make on a year-to-year basis, in any given year, even in their local area, they face a decision of choosing between hundreds of different varieties of corn varieties to choose from. And all of these varieties, a lot of them have relatively short life cycles. So on average, a given variety has about a 6-year average commercial lifespan. So they have these new varieties shuffling in and out of the market. And seeding rates themselves are not only specific to a variety, but they're highly specific to that farmer's region. So, they're facing this choice where new varieties are coming in and out. They've got their specific growing conditions in their own land. Ultimately, what that boils down to is that the seeding rate choice, how many, and let me just say a moment here. So there's, what I'm going to look at here is called a planting density or seeding rate. And this is slightly different from plant population, what I just mentioned before. So plant population is how many plants are standing at the end of the season. Seeding density is how many seeds a farmer puts down at the beginning of the growing season. They're going to be super close because, generally speaking, the germination rate, or the rate at which seeds become successful plants, is usually exceeds 98%. So they're very close. But in any case, what I'm going to look at with our data is we see seeding rates. So the seeding rate choice is, given all these factors, it's a super, it's sort of complex and uncertain in nature. And so it's something that there's always a lot of uncertainty surrounding. What should I plant this new variety at? Do I just plant it what the company tells me? And what have I planted in the past? What is basically going to produce the best yield for me or be the most profitable seeding rate to choose? And so with this in mind, the objective of this study is to shed more light on this whole process. And in particular, we wanted to know whether and how farmers learn about this optimal planting or seeding rate over time. And as an offshoot of that, what we'll see is that, is there sort of a bias to this learning, in the sense that is there an inefficiency to the way that this learning has occurred? And, you know, if indeed there is, could this be improved through certain policies or investments? So let me just put a picture to this relationship between plant population and yields. So going back, this is plant population. So what the blue line here shows, and this is USDA NASS data. This isn't data that I'll be using, but this is USDA NASS data. The blue line shows yields over time, and the red line shows plant population. So you can really see how tied together these things are. Now, I'm not suggesting that this is just like a causal thing, like it's just a matter of you plant more, you get more yield. That's not how it works. But there is this tight relationship between the two. And so you can see yields, you've got this year-to-year variation, of course, because of weather. But with plant population, you also have this sort of steady, almost linear increase in plant population over time. And as another just offshoot of this, something I've given some thought to, I've discussed some other people with this, is that it's interesting with corn is that this mechanism of that increasing yields has essentially always gone along with packing more plants in the same amount of surface area. Is what does this mean for the future? So, you know, in principle, there's got to be some limit to how many plants we can pack into the same amount of surface area. It can't, you know, there's only so much, only so many stocks you can sort of fit in. So if this has been the trend, what is this going to look like 50 years from now? And presumably, if this has always been sort of how we've gotten increased yields, at some point there's got to be a ceiling to this. In any case, this is sort of this, the background, the underlying relationship, and why we wanted to understand how farmers figure out, not just farmers, but also breeders, companies themselves. I mean, they do limited trials. There's only so much they can do to assess what the optimal planting rate or seeding rate is for a particular variety. And so what is the nature of this? How does this occur over time? So before I jump into, you know, sort of a simple model of what we did, just a little bit about the background and the literature that's related to this paper. So there's a lot of, it sort of draws on different strands of literature. So one big strand of the literature that this is related to is the agronomy literature. And so what the agronomy literature said is, you might ask, so why is there this relationship between planting rates and corn? And one reason you have this relationship is that corn is actually unique in some ways compared to other crops, for example, soybeans, in the sense that it is not as responsive to environmental stress or environmental constraints as some other crops. For example, soybeans, you plant them at lower densities, they'll compensate more, they're more bushy, they'll grow more, they'll yield more. Whereas if you pack them all together, then they'll compensate down and they won't grow as much. So the variation in yield isn't as much. Whereas corn, you put it in different environments, it will change more. And so really there's been a lot of work in agronomy to, you know, understand why yields have increased so much. And as it relates to density, there's two researchers in particular who I highlight here. Russell, he's got a paper in 1991 that summarizes this nicely. And then Don Duvik, who is at Iowa State, did a lot of experiments on this. And one way they teased out this relationship between planting rates or densities and yields is they did some basic experiments. So what they took is they took different hybrids from different eras. Like you take a hybrid, say, that was bred in the 1960s, one in the 70s, 80s, 90s, so more modern and older hybrids, and then they planted them at different densities or different planting rates. And the idea here is that you're planting them at different levels of environmental stress and water stress and constraints, and then they compared what their yields were. And so what they found was that at low densities, where there's not that much environmental or water stress, there was a yield advantage to newer hybrids, but it actually wasn't that large, not as large as you expect given the increase in yields. But when you started increasing the density, when you started putting more and more stress, that's where you really started to see the advantage of newer hybrids. And so this is really the fundamental underlying reason for why you have this relationship between yields and density, is that newer hybrids newer corn varieties are really just much better able to tolerate competition and stress between other plants without sacrificing much yield. Now, another strand of literature that this paper is related to and draws on is there's a really big development literature on learning and crop production. So I've got a big list here. Some of you may have read some of these papers. Foster and Reisenzweig, 1995 is a big paper. Conley and Udry, Dufflo, Kramer, Robinson, Dufflo, the recent Nobel. They've done a lot of work. This is big in the development literature because what they find is that in developing countries, there seems to be under-adoption of hybrid varieties or really high-yielding varieties. There seems to be underuse of certain inputs. And so that what they've wanted to understand there is whether and how farmers learn about the adoption of these new and better hybrid varieties, and whether and how they learn about, fertilizer use. And so, for example, in I think it's Dufflo, Kramer, and Robinson, they find that I think it's in Africa, farmers tend to, it at least appears on the face of it, that they underutilize fertilizer. They underinvest in it. They should be using more. That if they were to take the out-of-pocket expenses, it would be worth the extra dollars they use to use that fertilizer and get the extra yield. But in fact, they don't. So this has been a big topic of study in development literature. A lot of this they use using experimental data, but none of these studies have looked at planting rates. And really, most of them don't focus on developed countries like the United States because, well, we tend to think of, producers and farmers in the United States being pretty efficient in their production practices. In any case, related to this, one of the things a lot of these, the learning studies do is when they want to try to figure out whether learning has taken place, is there's a couple of really key testable predictions. Sort of at the heart of these studies is what they use to try and figure out whether farmers are learning. And so the first is this: if productivity increases for a fixed technology over time, that on the face of it is strong a priori evidence that learning is occurring. And the way to think about this is, say you got a machine, it comes out in year one, and you have workers producing some product with that machine. 10 years later, you look at the productivity of that machine, and productivity has doubled. And it's the same machine, nothing has changed. The simplest explanation for what's happened in that case is that they have learned how to better use the machine over that 10 years or whatever course of time it has occurred. So the basic idea here is if you see that productivity increases for a fixed technology over time, a very likely explanation for that is that some kind of learning has taken place. Now, another explanation for that is that the optimal input use or something else about the machine has changed over time. And so empirically speaking, that's always the most difficult aspect you have to deal with in trying to assess whether learning has actually occurred. Now, in our context, if we were to apply that logic, we would want to say, look at whether yields have increased for a fixed technology over time, say a given corn variety. But in our case, we don't actually observe, in the data set that I use, we don't directly observe what the yield is. So that's not an approach we can take. But an alternative approach that is quite related, and this is one aspect of Conley and Udry, they looked at pineapple farmers, is that it's also learning would appear likely to be present if you see that for, say again, a fixed technology, the producers or the workers are changing how much inputs they use with that technology over time. And so if they're using, if they start in year one and then by year 10, they're using a very different input rates or mixes with that, machine or whatever technology it is, 10 years later, that would suggest that they figured out that, they've learned that there are better ways to use those inputs or better rates at which they should use them. And that would be suggestive learning. Now, again, this is the critical aspect of this is that you've got to, condition or control for other possible factors. It may be that other market changes or something else has induced them to change the amount of inputs they use. And so in order to, sort of be convinced that learning has occurred in that circumstance, you've got to think about these other things. So let me, before I go to the next screen, in the context of our case, this is really sort of the basic idea of what we want to look at. We want to think about whether there's learning, and one of the aspects we want to think about is one signal that there would be learning is that if for a fixed technology, and here when I'm thinking of fixed technology, I'm thinking of a given corn variety, a given corn hybrid. If the input rate, and here I'm concerned with planting density or seeding rate, if that is changing significantly over time, and there's nothing else major going on, that suggests to me that there's likely learning occurring, okay? And so this is one of the key figures in the paper. I think it's actually the most important figure in the paper to sort of just give a visual depiction of what I think shows that there's probably this type of learning that's occurring with respect to planting rates or planting density in the corn market. So what this picture shows is what I looked at is I took the 15 most purchased corn hybrids or varieties in the United States. And what this plots is it's a fitted trend line to the planting rate over time with a 95% confidence interval. I did restrict it in this case just to Iowa because I wanted to avoid issues of heterogeneity. But if you extend this to the entire United States, it looks pretty much the same. And really what, when I was first looking at all this, this is what really suggested to me that there's some type of learning or there's information acquisition happening here, is that almost without exception, in almost every single case, for every hybrid, you see that there is a significant increasing trend of planting rates over time. So like this top panel is all Pioneer hybrids. This bottom panel is DeKalb hybrids, who would have been marketed by Monsanto. The one exception is there is a slight downward trend here for this Pioneer hybrid, but otherwise it's always increasing. So what this is essentially saying is that if you're a farmer producer, if you started out planting corn variety at say a particular planting rate, say it was 30,000 seeds per acre, if we were to check up on you 5 or 10 years later, we would almost invariably find that you're planting that at a significantly higher rate, say 1,000 or 2,000 kernels higher. And so what this suggests to me is that this is pretty strong a priori evidence that learning is occurring. Now, the one possibility is that there are other things going on that would make all producers want to increase rates. For example, if prices were changing in some systematic way, or they were all, say, going up to encourage higher planting rates, that's one possibility that might encourage. Or say there was some other technological change that would change to make them all do this. But if there's not such things, this suggests to me that that there's, and it's not just that learning may be occurring, that it seems to be happening with like a systematic bias. It's not that sometimes they're starting way too high and then they're going low. It's that they're almost always starting too low and they're ending up much higher 5 to 10 years later than where they started. So, and this is like persistent. It's almost like if I were a farmer in 2000 and I knew this was always happening, if you were perfectly rational and you knew this trend was always happening, you should sort of shift up. But of course, these varieties are always coming onto the market and they have relatively short lifespans. And so I think it's fairly plausible that they're sort of just going on what they've done in the past and then updating as they go. And this is not just farmers who are learning about it. This is breeders, this is seed companies, this is extension. They all have relatively limited information when it comes to what is the optimal seeding rate for a particular variety. You can only test this, you can only do so many variations in different conditions. So it's really ultimately, even though they may have a recommendation from the seed company, that information is based on relatively. And to add to that, farmers are already relatively skeptical of what the seed company is going to tell them, because more seed costs more money. And so if the seed company is telling them, you should be going at 30,000, but you've been doing 28,000, they're going to be reticent to do that because it's going to cost them the extra money to do that. In any case, it appears to be the case that they always increase rates like this. So this is this visual depiction sort of forms the basis of what the empirical analysis is going to look at. and try to sort of just tease out in more detail. Basically, it's going to amount to looking at it in this way, but controlling for other potential factors that may influence the seeding rate over time. So to motivate the empirical model, what we did in this paper was we developed a simple farmer model. And the idea here is we're going to have a simple model of profit maximization and with learning to motivate the empirical approach we take to sort of test whether learning has occurred over time. And so
hey, Ed, my wish has a question. Is now an okay time?
Yeah, sure.
All right. All right, you're unmuted, my wish.
Yeah, I'm so sorry. I couldn't figure out the chat box, so I had to raise my hands. And it was related to the previous slide where, yeah, you were showing the learning happening and the line were increasing the trend.
Yeah.
Do you know where the recommendation, if you were to put a recommendation line, where would that fall on these graphs? Would it be quite in the middle, on the top, below even the starting rate?
Oh, that's a good question. You know, in the data, I don't see what the recommended planting rate was. And I think it would be, I can see what the variety was. It'd be a tall task to try and match these varieties to what was recommended for them, in fact, you know, at the time of planting. I don't even know if that's available on the internet. You know, a lot of these farmers, they deal with their own dealers, and you know, maybe the dealers will tell them what they should be planting at, or maybe the seed will come with a certain recommendation. But yeah, I don't know what the recommended rate was.
Sure. Yeah, I mean, the motivation for that question was for learning to happen, there has to be some base knowledge with which you start. And then, you know, you update that based on your experience. And that's the learning that's happening. And I was just wondering whether that base knowledge, the source for that base knowledge would be what is recommended by the seller or the company or the extension agents, you know, that are promoting those varieties, and, you know, how that the starting year planting rate compares to that base knowledge.
Yeah, I mean, that's a good question. I don't know the exact answer to what. I think a lot of times they will buy these varieties and they will have recommended rates. But I would even say with there is extension information out there. There's trial information they can access if they go online. Like if you go on to Pioneer's website right now, they now all of these companies, and I don't know how long they've done this for, I think it's been for at least 5 years, they have planting rate calculators. So you can go onto these, you can pick the variety you're going to plant, you can tell them where you're located, and then they will give you a suggested planting rate. And the one thing I would say about this is that I think, you know, even these recommendations by these companies are based on their own sort of limited testing. So they have, I think the companies, they do testing on what different rates produce the highest yields, but they can only test them in so many locations and only so many variations. So, and even with that, and now some of these websites, what they actually do is, I've seen that they're actually taking, producers and farmers themselves can report the yields they've gotten with their own planting rates to this database. And so then you can see what other farmers have got who've used this variety, what yields they've gotten from this planting rate. And so that suggests to me that, you know, even, you know, the company has limited information, farmers have limited information, but yeah, they do. My guess would be that the baseline they're going from is sort of their own experiences in the past, and they weight that against what the companies recommend to them and so forth. So.
Thank you.
Yep. Yeah, so to sort of, to put a model to this and to sort of motivate what we do for the empirical exercise, we develop a sort of a super simple model of farmer profit maximization with learning in it, okay? So we're going to start with the base assumption that farmers are risk neutral profit maximizers. And I will relax that, or I'll talk about the possibility of risk aversion, because a lot would argue that farmers are risk averse, and so I'll allow for that later. But it is actually quite common in this literature to assume that farmers are risk neutral, and that's sort of what we start as a baseline. And so we start with their risk neutral profit maximizers. We're going to assume the yield function, the per acre yield function, is quadratic in seeding rates. This is borne out by some agronomy research in recent years. So AFRE, they did a couple of papers on this where they have like over 100,000 observations where they fit yield functions to seeding density, and they find that the best fitting function is a quadratic function. So we're going to assume that yields are quadratic in the planting rate, and so here we have, this is the quadratic function here. So y is yield, z is the seeding rate, theta and beta parameters, and what you get out of this, you do first order condition, you're going to see that theta is what's called, what you see in the agronomy literature called the agronomic optimal planting density. And so this is not necessarily the economically optimal planting density, but it is what maximize yields. So we're going to suppose from the farmer's perspective, this is something they don't know. They have, they may have guesses about it, but from their perspective, it's a random variable. And so theta bar then is their expected agronomic optimal planting density, conditional on any information that they have prior to that, or that they have, given what the seed companies have told them and so forth, okay? So given that, then they're going to maximize expected profit. We're going to extract from other inputs. For now, we'll think about those more in the empirical model. So profit here is just going to be price times quantity minus the cost of the seed. And so P is the price of corn, W is the price of seed per acre. And if you take first order conditions with this, since the only uncertain variable is in the expected agronomic optimal density, you get a nice simple solution here. And the economically optimal density is then going to be the agronomic optimal density offset by the effect that prices can have on what you should select. So I mean, this is a simple, straightforward solution. It's saying that, if seed prices, which represent by W, if they're higher, you're going to want to plant a lower seeding density, whereas if output prices are higher, you're going to want to plant at a higher density, okay? And so you've got this basic case where this is the optimal seeding density is a linear function of what you expect, or whatever, given your information, what you know about the agronomic AOPD, the agronomic optimal planting density is, and the ratio of input to output prices. And so then the idea is the farmers have their best expectation of what this is, and they're going to update their planting rate, the optimal planting rate, on the basis of their beliefs about this agronomic optimal planting density, okay? And so then you can take this simple, and then you can embed a little bit of learning in it. So we're going to do a simple Bayesian learning case. And the idea here is that at time t equals to 0, or you could think of it at whatever time of variety j it comes to market, I'm going to suppose that farmers have heterogeneous plots, which we denote by I. We're going to suppose that the true, to keep it simple, this is, we're using this as motivation, the true agronomic optimal density is given by, which is given by theta ij, is going to be specific to the variety itself and also to the farm, okay? So you will have this factor that, if you're a farmer in Iowa, you're going to want your optimal density is going to be different than if you're in Kansas for the same variety, okay? And then at periods t, subsequent to that, as each farmer receives signals, and these signals can be their own signal, they can be signals from others, they're going to receive a signal about what is the actual optimal density, the optimal seeding rate associated with that variety. And so the thing about this signal, though, is it's composed of two components. It's composed of what the actual optimal planting rate is, but it's also got a noisy term in it, okay? And this noise is the fact that, you know, weather varies year to year. You don't know if your conditions apply to your neighbor's conditions and so forth. The fact is that you get some signal about whether this was a good planting rate to choose, but you're not exactly certain about whether the information you've received tells you exactly about the optimal density. And so you have this basic setup. You have the true optimal density, you have the fact that they're receiving these signals, and now we want to know how are they going to update their expectations about this optimal density over time. Okay, how are they going to update their beliefs about theta ij, which goes back to that first order condition. And so standard assumption what makes things nice and neat, is that, you know, we're going to assume they've got to start by what Miłosz said, is that you've got to start with what do they expect from the get-go. And so each farmer has, or producer has, their prior, which is theta ig here, ij, their prior about what they expect the optimal density to be. And so we're going to assume that's normally distributed, and we're not going to constrain the prior. We're not going to assume that it's correct necessarily on average. It's that they have a normal prior theta ij 0, and they also have a prior, what you would call perception variance around it. So they have some expectation about what it is and some expected spread in some sense about what the optimal density is. And then we're also going to suppose that the noise is also distributed normally with mean 0 and the time invariant variance around it. So you take these two things into account. And so we have the distributions of what farmers believe sort of from the get-go. They're prior about what is the optimal density and the fact that you have this noise involved in the signals they receive. And if you assume that they're Bayesian learners, then you can do some manipulation, some algebra, and you can get updating equations for how over time their beliefs about the optimal density and the spread of that density changes over time. So what this says is if you just do a bit of manipulation, you see their expectation of what the optimal density is a function of what they expected it to be in the previous period, weighted by the variances, and also then weighted by what the information they just got in the current period. And the perception variance itself is also a combination of these variances over time. And what this N of t here represents, this is the number of signals received by a farmer about what the optimal planting rate is, okay? And so a little bit more about, in this paper, we are agnostic about what the nature of these signals are. We're not taking a stance on whether they're solely from individual experiences you have with planting it, or whether it's, you know, you've seen your neighbors plant a particular variety or similar varieties, or whether it's the company who's done trials or breeder extension experiences. It's basically, N of t represents signals you received from somewhere about what the optimal planting rate is associated with this particular variety for your particular location. And so you get these updating processes, and then what they imply, there's a couple of implications or predictions associated with this Bayesian learning process, okay? So the first main implication for the purposes of our empirical analysis, and it goes back to the second equation here, the perception variance, kind of the spread you have around what you think is the optimal planting rate. As you get more signals, as more information is acquired, the perception variance, or the belief about the true agronomic optimal planting density, it decreases over time. And as in the limit, as those signals go to infinity, it will converge to 0. So it'll just tighten around the 1. And related to that, implication number 2 is that as you get more information, the mean of the posterior distribution, the mean of what you expect to be the agronomic optimal planting density, that converges to the truth, okay? And then because we've assumed here that we're not constraining the prior to be correct or incorrect, that it could approach the truth from above or below. It could be the case that farmers, they're too low to begin, or they're too high to begin. We're not necessarily saying that they're correct from the onset, okay? So that's sort of the two main implications that we you know, the idea of this model is to motivate what we do, and these are the two main implications that come from that. And so just to put it a little bit more, I want to translate that to what we do with the empirical model and how that's going to work. So the first is that with the first implication, if learning is present, then we would expect to see that the variance in planting rates for a particular variety should decline over time. In other words, if you took a farmer and they were planting this variety, you know, over time, we should see that, or you had multiple farmers with the same land conditions, we should see that the spread or the variance in their planting rates as they learn more and more is shrinking closer and closer and getting tighter as they get closer to that truth. So that's like an empirical test that we're going to use to see if we think there's learning going on. Basically that the variance in planting rates is shrinking. And then secondly, if, and this is related to more how the mean is updating, how their expectations about the optimal rate is changing over time. If indeed they do, or they are essentially, say farmers are on average hitting the correct optimal rate for a particular variety, we shouldn't observe a significant change in the mean planting rate for a particular variety over time. Conditional, and in an empirical model, that's going to be conditional on, you got to have variety fixed effects. And I'll talk a bit more about that in a second. And so the idea here is if they were correct on average from the get-go, you shouldn't see much of a trend in planting rates for a particular variety. But of course, that's conditional on other factors that potentially changing, for example, prices. And then a third sort of related to that offshoot is that if they are persistently underinvesting in seeding rates, then we would observe that the planting rate for a given variety is rising over time. If they were overinvesting, we'd see the opposite trend. But if we see that for a particular variety, what this model, the basic Bayesian model suggests, is that if that rate is going up, then it suggests that they're, you know, sort of persistently underinvesting in seeding rates over time. All right, so given this, the Bayesian model, the sort of the setup, it would serve as sort of a guide. We then wanted to take this to a way we could test this in a simple way with regression analysis. Okay, and so we do this in really two different ways. So the first is we estimate a basic linear regression model, and the model is described here. And so the main dependent variable is, I'll talk a bit more about the data in a moment, but the main dependent variable is the observed planting rate on a particular plot for a particular variety in a particular year. And we're going to regress that on the commercial age of that variety in that year. So this commercial age, this is basically our primary variable of interest. And it's what we are proxying the amount of information for. The idea here is that the longer a variety has been commercially available, the more information farmers will have acquired about this particular variety. We consider actually, ideally what we would have done with this is you can do this all at the individual level. So we would, for example, see an individual farmer, we would see how many times they've planted a particular variety, and the more experiences they've had with it, we could look at it in the same way. But as we'll see in a moment, what we have is an unbalanced panel. So for a lot of farmers, we do have some repeated observations for some farmers, but for a lot we don't. And so we have gaps in the years they spend, so we don't really know exactly how many years of experience they've had. So as a result, what we did was we used this commercial age variable to proxy for that level of information. And then the idea here is this is going to tell us, this is going to sort of say, all right, in principle, if you have more, if this variety has been commercially available for a longer period of time, if there is no learning occurring, then this coefficient should not be statistically significant. You shouldn't observe a significant difference in planting rates for this particular variety over time if they're sort of starting at the correct rate. Now, critical to this, and I'll just jump ahead to the other thing, is these seed variety fixed effects. Okay, so it wouldn't make much sense to think about that if we didn't have these variety fixed effects in there. But we're going to be conditioning on the seed variety that as a farmer a farmer is planting. So the idea to think of it is that, so for a particular variety, do we see that seeding rates are increasing over time? And in this baseline analysis, we're forcing the beta coefficient to change at the same rate for all varieties. I'll relax that later and show how for different varieties it changes. But the idea here is that we're going to, at least at the initial stage, assume. So you can kind of think of this as like, the beta is kind of like an average of the rate at which seeding rates are changing as a function of commercial age over time for a particular variety. Now the other variables we want to include in here as controls is the most basic one is that, of course, given the, what we know about, if we're assuming farmers are profit maximizers, we also want to control for prices. So we also include in here, given the first order conditions of the profit maximization problem, we include the ratio of seed prices to output prices. So that is given by R here. And then another important thing that we want to condition on and control for, although I said it's an unbalanced panel, we can still do this with an unbalanced panel, is we want to include farmer fixed effects. And the reason you want to do this is because a lot of times these varieties are introduced in certain regions first. Say they're introduced in the most productive regions like the Central Corn Belt, and they disperse to outer regions like the Fringe or places outside of that. And if you were just to do cross comparisons of seeding rates between what they plant in the Central Corn Belt versus say what they plant in a place like Kansas, and the fact that they're introduced at these different time periods, it might artificially appear that, say, planting rates are going down or not going up as much. But that would be because, planting rates in Kansas are lower than they are in Iowa. It wouldn't be indicative of the fact that how planting rates are going in Iowa itself. So this is the basic, the baseline empirical model for sort of just seeing whether this mean effect is changing over time. And then as an offshoot of that, we want to test that first implication back here. Is the perception variance, or is the variance of planting rates, is it decreasing over time? Or is the planting rate for a particular variety, is it sort of narrowing and having a tighter spread? And so to do that, we looked at it a couple different ways. One is you can just look directly at the standard deviation of planting rates for a particular variety. We've done it that way. But another way you can do it here is basically just to look at whether the squared residuals, or look at whether there's heteroskedasticity in the commercial age variable. So the basic idea here is you estimate this first model, then you take the squared residuals from it, and then you regress it on the commercial age plus the fixed effects. And if this parameter on the age variable is negative, that suggests that the conditioned on the variety, the variance, the predicted variance of planting rates is shrinking over time, which would be evidence of the fact that they're figuring out across the population of farmers, they're sort of figuring out that what the optimal planting rate is. So that's sort of the empirical setup, the two basic things we want to test with the empirical model. Okay, so to do this, we used proprietary data. And so this data comes, if some of you have used this data before, it comes from a company called Kinetech USA. And this data set itself is the corn track data set. And so what this data set consists of is about 4,733 randomly sampled farm surveys per year. And when they sample a farm, there can be, they purchase multiple varieties per farm. And this is for the period 1995 to 2016. And so what we observe for each farmer is we see what they plant, the planting rate for a particular variety they planted. We see the identity of that variety, which permits the variety fixed effects. And we see the price they paid for that seed. And then again, to reiterate, this is not a balanced panel, but they do resurvey a lot of, and we see the identity, not the identity, but we have an identity, a variable, just like an ID number. We can see when farmers are surveyed multiple years. And so then we can use that as well to include farm fixed effects. And so in total, when we take all the data together, we're going to estimate these models with about 400,000 observations during this 1995 to 2016 period. So here's just summary statistics for the variables that are used. Almost all of them are used in the model. So the first is the main dependent variable. This is the planting rate. Okay. So I've broken this down just to show you the difference between the central corn belt and the non-central corn belt. And so overall, during the period we consider 1995-2016, the average planting rate is about 29,532 seeds per acre. But if you look in the central corn belt, which includes Iowa, Illinois, Indiana, the southern crop districts of Minnesota, Wisconsin, that it is significantly higher than outside of that. So it's about 31,047 compared to about 28,000 for the fringe. Okay, and so that makes agronomic sense. In the central corn belt, the soil is most fertile there. You have good, the water stress is not as much of an issue there. It makes sense to plant at a higher rate in the central corn belt as compared to the fringe. Some of these others, so the commercial age variable, the main variable that we're using to proxy for information on average is 2.8. Another variable I've put in here, which doesn't enter into the empirical analysis, but just to give you an idea, is the average life cycle of a seed variety. So the average life cycle is we just take the first year we see it appear in the data and the last year that it exits, and on average it's about 6.3 years. Okay, so it's relatively, that means that, a variety comes on the market, on average it's going to be gone within 6 years. But there are some varieties that are super successful, and they're actually in the full, all 22 years of the data we look at, whereas other varieties, they have limited success, they don't have much adoption, they're only there for a single year. Seed prices average about $155 per bag, which is 80,000 kernels. We got the corn futures price. This is something we brought in to supplement the Kinetech data with to get that ratio of seed prices. These are just national corn futures prices. On average during this period is $3.73, and then the price ratio averaged about $4.62. And then two other variables that we bring in for robustness checks. A thing I mentioned previously is that if you want to try and tease out whether there's learning there, and you're looking at this commercial age variable, the problem is that you have potential confounding, unobserved confounding factors that may have also encouraged increasing seeding rates. And so we've looked into this industry, thought a lot about what are the other possible things that could possibly impact the seeding rate in this market. So one is that reduced till or no till became more common during the period we consider. So that was one thing we want to control for, because in the agronomy literature they argue that sometimes conservation tillage can change the optimal seeding rate you want to use. And another is neonicotinoid seed treatments. So neonicotinoid seed treatments are an insecticide applied to the seeds that became really prevalent during the period. And some would argue they also may change the desired seeding rate. So for example, if you can protect the seed better and you have a higher chance of it germinating and becoming a plant, then perhaps you need to plant at a lower planting rate if you have a seed treatment on it. So these are going to be two additional control variables I introduce into the analysis.
Hey, Ed, we've got a question here from MyWish, which says, what explains the zero seed prices in your data?
Oh yeah, so some farmers, I don't know if it's, if it's like a discount bundle deal, but in some cases they will get, at least in the data it's recorded as paying zero for the seed. So I've done the analysis both including observations that have these zero seed prices and excluding them. It doesn't really change anything. But yeah, I think there are some cases where maybe they get a bundle deal where they buy a certain amount of a seed variety, and as a bundle deal you get free seed for some other thing. So that's, unless, I mean, there is of course the possibility that's an error in the survey, but that's been my interpretation of it.
Great, thanks.
Yep. All right, so here are the baseline regression results. So by baseline, I mean, if we go back to this regression model here, these are the results associated with the regression of planting rates on commercial age, the ratio of seed prices, and so forth. And so I've presented 4 cases here. And the reason I present 4K is I just want to show the significant effect that including different levels of fixed effects have on the results. So our most preferred specification, the specification that we think is most reasonable because of the fixed effects included, is the fourth one. And that includes both variety fixed effects and farmer fixed effects. But what's interesting to see about this is that in the first column, we don't include any fixed effects, neither variety or farmer. And you can see kind of the wonky results that you get if you do that. So if you just regress seeding rate on the price ratio, the commercial age of the variety, and you get a constant in there, you get that with each additional commercial year that variety has been a variable, they're actually decreasing seeding rates. And the crazier result is that this price ratio is like very large and positive, which is counterintuitive to what you would expect, because you'd expect that if the seed price, which is represented by W, if that's higher, you would expect farmers to reduce, relative to output prices, reduce their seeding rate, whereas this suggests that they actually increase it. So I think that this is just to demonstrate the importance of, you've got a condition on the variety that they're planting. Once you do this, the price ratio goes, it becomes insignificant, the commercial age flips sign and becomes statistically positive at 92. So this says that with each commercial year of availability, the seeding density increases by 92 kernels per acre. And then now in the next two columns, I introduce regional and then farmer fixed effects. So this one just introduces agricultural district fixed effects, which is sort of one level of the control for this fact that, you know, different districts plant at different rates. So really what you want to be doing is making within comparisons. And here now, as you do this, the price ratio becomes negative insignificant, the commercial age coefficient goes more. And then if you get all the way to the level of where you've also got farmer fixed effects, you see that now it's increased all the way up to 222 kernels per acre, which is actually what you see. If you just look empirically at the trend in planting rates or seeding rates over time, it's about 200 kernels per acre. And so what this suggests is that the main takeaway from this, and it's kind of like that figure I showed earlier, is that if you look within a variety, even if you condition on prices and you condition on the location, the farmer themselves, they're really, from one year to the next, they're increasing seeding rates over time. Where they start, say, in year one, if you look at them 5 years later, on average, you're going to be planting that same variety at about 1,000 kernels greater than they were 5 years ago. So that to me is, that is, you know, if you think about it within the context of the Bayesian learning model, one, that suggests that some type of learning is occurring, but two, it suggests that there's this sort of persistent downward bias in where they start in their planting rates. They have sort of this chronic tendency to chronically underinvest and always catch up to the correct seeding rate. All right, so this is the basic linear model. And what we did is we looked at the heteroscedastic aspect. And here again, what we're doing is we're taking the squared residuals from that initial model, and then we're regressing it on the commercial age of the seed variety, and while also conditioning on the variety and farmer. And so here we again find what would be consistent with the learning process is that as you increase the commercial age of the variety, the variance, or the predicted variance in seeding rates is going down over time at about a 4% rate per year. So, you know, that's a reasonably significant rate. So taken together, both of these things, they suggest that, you know, learning certainly seems to be within the context of the Bayesian model is set up. It seems to be very much present, but it also seems to be occurring with a bias in the sense that they're starting too low and they're catching up to what the appropriate rate is. And the interesting thing is that actually, if you sort of look around at farmer forums and so forth, a lot of them will express this skepticism that what the seeding company is telling them to do is too high. They want them to plant at too high of rates. But if you just look empirically at what's actually happening, is that they seem to be, you know, over time actually increasing the rates. So At least during the period we consider, it seems to suggest they were usually too low. Okay, so what we wanted to do next is I've talked about, so the one thing that is you know, to have sort of confidence in the fact that you see these increasing rates, is there anything else going on in the industry that would prompt producers to increase their seeding rates over time for a particular variety, besides the fact that they're learning? Like, are there just other, like, we've conditioned on prices, so those wouldn't be the case, but other things. So two major, I mentioned these before, two major things that we wanted to look at were the whether or not they have a neonicotinoid seed treatment or whether they use reduced till. So what this table shows, this is what we did, is some robustness results. I'll also talk a little bit about an expansion of the results we looked at. What this first column looks at is, so one thorny detail that I didn't mention, when you're constructing these data sets and you want to do, when you're computing, say, the commercial age of a variety or the lifespan, is you run into the problem of the fact that at the beginning of the data, you have observations on seed varieties that were likely already on the market for years before. So like we started in 1995, and say we see a variety then. All that I can do at that point is say that that variety has a commercial age of 1, but it's very likely that if it's there, it was probably there in the year before or multiple years before. So in some sense, it's a censoring problem or a truncation problem. We don't know exactly what the commercial age of the varieties were in the early years of our sample. So what this first column does is I remove essentially varieties in the first 5 years of our sample, and I only look at varieties that were introduced subsequently to that to sort of see if that affects the results we're getting for the commercial age coefficient. You can see it doesn't really, it's very slightly different, but by and large, it's about the same as it was before. The next two columns introduce these additional control variables for possible factors that could have influenced the seeding rate over time. So this first one looks at the neonics share. So what we did here is we looked in a district that a farmer resides in, and we looked at what is the share of seed that was planted that had a neonicotinoid seed treatment. And the idea here is that if that does influence the seeding rate, this would control for that fact. So when we put that in, we find in that case that it's insignificant and doesn't really affect the commercial age coefficient. And similarly, we also looked at within an agricultural district, what is the share of farms that used reduced till, as that could possibly impact what they do with their planters. And here we actually found that, and it's a little bit, this is one result that I'm not, I haven't quite sorted out, and it's maybe a little bit counterintuitive to what I expected, is that if you have a higher share of farms or land with reduced till, they're using a slightly lower seeding rates. Whereas I would have sort of expected that if you have more conservation tillage, perhaps you would compensate with that by having a higher seeding rate. In any case, the main implication for ours is that it's not really correlated with the commercial age variable, so it doesn't really affect that. Now, these final three columns are not really robustness checks. What we wanted to do here is we wanted to see whether there were sort of different rates of planting rate changes for different regions, and then depending on what type of farm you were. So in the fourth and fifth column, we estimated separately the same models, one for the central corn belt and one for the non-central corn belt. We estimated those same models. So what we can see here is kind of consistent with the summary statistics, or it is consistent, is that in the central corn belt, they're just on this general faster upward trajectory. And so for a given variety, they're increasing seeding rates at a faster rate than they are in the non-central corn belt. And then with respect to farm size, this was kind of interesting because we wanted to see, there's some previous literature that suggests that smaller farms, because they say plant less varieties, they have less resources, you know, investments, it takes big investments to learn things, that they may learn at different rates, and usually you would expect perhaps learn at lower rates or not have as much information from the get-go as larger operations. And so what we find here is that if you're a really small operation, you're planting less than 100 corn acres, your rate of updating is actually much higher than your rate of updating if you have an operation where you have more than 1,000 corn acres. And as a supplement to this, it's not shown here, is that you can also compute what is sort of the average starting point. Where do they start at with their average planting rate? And so for small operations, they start much lower. So they start, in some sense, I would say farther from the truth, but they update faster. Whereas larger operations, they start closer to the truth, but they update slower. And in some sense, I find that perhaps kind of intuitive, because larger operations are probably planting more different varieties. They may have more access to certain types of information. And so they're already starting closer to perhaps what is optimal, and then they don't have to adjust as much, whereas smaller farms are starting farther from it. All right, so with this baseline model, as I mentioned before, I fixed this commercial age coefficient. Even though I'm conditioning on variety fixed effects, I fixed it to be the same for all varieties. But like in a Bayesian learning model, for example, the way we sort of motivated it or thought of it is that it's for a particular variety. So for a particular variety, how much do farmers update or change their seed planting rates over time? And so as an offshoot of this, what I did was I estimated separately these same regressions for different varieties. And what I did here was I just took the top 15 hybrids, the same hybrids that I showed in the figure earlier in the presentation. I took those 15 top hybrids and I estimated those regressions separately for each of them to see if there's much variation in the rate at which farmers update their planting rates as a variety has been in response to its commercial length. And so what we see here, and all of these regressions, they all include farmer fixed effects. They all have a price ratio variable, so they're the same as before. The one difference is, of course, they don't have variety fixed effects because it's a variety specific regression. But the main takeaway for me from this is that, you know, without exception, the trend, if you do these within variety regressions, is invariably positive. There are two cases. This DeKalb variety here is barely positive and statistically insignificant, and this Pioneer variety here is also positive but statistically insignificant. Otherwise, it is always the case for if you do these variety-specific regressions that they're always tending to increase these seeding rates over time. There is some heterogeneity. For example, here you've got 180, whereas some you've got as high as 375 kernels. But yeah, I think this, to me, these variety-specific regressions sort of just reinforce the baseline regressions where you're forcing that updating to be the same across all varieties. Okay.
Ed, it looks like quickly
yeah.
we've got another question from Eric Crawford here, which says, about the commercial age of varieties in early years, could you not have determined their age through historical info from seed companies, extension services, or other places?
Yeah, it's possible. I suppose, you know, you go back to 1995. I don't know what information was available on the internet then, whether you could scour the internet and try and see. I mean, it's not like, if you look at a lot of these varieties, even the places that report characteristics about the varieties, for example, UW-Madison, they report field trials for a lot of varieties, and they give a lot of information about it. But one thing I've not seen anywhere reported is the year that they were commercially released. So maybe in principle, it's possible if you contacted every company and asked them about the inception date of that variety, but it's certainly, it would be, in my view, it's, it wouldn't be worth the time to go into all that trouble. Rather, you just look at whether taking out those cases significantly affects the results.
Thanks.
Yep. Okay, so I want to get back to this case of the possibility of risk aversion. So in that baseline model, the little toy Bayesian model we set up, we assumed farmers were risk neutral. And when you do that, basically the implication is that if you observe these positive within variety trends, that implies sort of a biased prior. But an alternative possibility is that farmers are risk averse, and if you allow for that possibility, then if you go into the literature and you write out a model, that would show that a risk averse farmer compared to a risk neutral farmer would choose, if you have a quadratic yield function, would choose a seeding rate, an optimal seeding rate below the seeding rate of a risk neutral farmer. And as they acquire more and more information about the appropriate seeding rate, they would revise that, as a risk averse farmer, they would revise that optimal seeding rate upwards. So these within variety trends we see for these seeding rates, it could be due to the fact that farmers are risk averse and they do know, or they are sort of correct on average, but because they're risk averse, they choose a lower rate than is the true optimal rate. And so that is, that's probably been one of the things we've thought about most about, can we say whether what we found is evidence of a biased prior, is it evidence of risk aversion? And really the tricky thing about that with our case is that, and I've looked into this a bit about trying to estimate some of these models, is that given our data, it's really, and in general, it's really difficult to disentangle identifying the prior separately from the presence of risk aversion. This is not just a problem for us, this is a problem that's common to previous studies. So for example, if you go a well-known paper in the learning literatures, Erdem and Key, 1995, and so if you go there, they assume, a common assumption will be you either assume an unbiased prior, like they're correct from the get-go, and then you are able to estimate the degree of risk aversion, or you assume risk neutrality and then you don't, you allow the prior to be estimated. And so the trick here is that we're not really able to directly disentangle one from the other. So what we did to try and get a bit of an idea here of whether risk aversion is an important factor in determining corn planting rates is we looked at the contrasting case of soybean planting rates. Okay, so with this data, it consists of both corn and soybeans. We have data on soybean planting rates as well. And the thing about soybeans is that they're also approximately, the yields are also approximately quadratic in seeding rates. So the idea here is that if indeed risk aversion is sort of an important factor in determining soybean seeding rates, then we should observe similar trends in soybeans, and that might suggest then that what we found is it could be risk aversion or it could be a biased prior. It would be difficult to say which. On the other hand, if we find that something completely different is happening for soybeans, that suggests to me that it's because the same farmers are planting soybeans, that risk aversion is not a major factor in determining these upward trends. And so, and the interesting thing about soybeans, just from an a priori perspective, is that I think for at least a decade or more than that, if you look at extension recommendations and so forth, they've been telling farmers they should reduce their seeding rates in soybeans. So in contrast to corn, they've been wanting them to go down, whereas corn is generally gone up. And so what we did here to look at this is we estimated the same planting rate models for soybeans that we did for corn to see what was happening for soybean seeding rates with US farmers. And so here's essentially the same set of the 4 regressions that we did for corn. Here we're just doing them for soybeans, okay? And the main takeaway from this is that it is the opposite, the exact opposite, consistent with what extension has been recommending for soybeans than it has been for corn. So actually, if you look in soybeans and you condition on variety fixed effects, soybean farmers have been reducing for each additional commercial year a soybean variety has on the market, they're actually reducing the rate at which they're planting soybeans. And so this suggests, you know, the flip side of this suggests that farmers are actually over-investing in soybeans, in seeding rates in soybeans. But it also, it suggests to me that, you know, it's difficult to rationalize risk aversion as a big driver of those upward trends in corn if you have this opposite trend in soybeans. One other thing I just wanted to note here that I didn't note for corn, but that's rather interesting and, compared to soybeans, that in corn, if you look, when we looked at the price ratio, that price ratio estimate was negative but marginally significant, and in terms of economic magnitude, very small. And so one of the small offshoots of this study is that it doesn't appear to be the case, at least with this data, that farmers care much about prices when they choose their seeding density. It really appears to be more the case that, at least presumably, they're just trying to hit the maximum yield. And if seed prices go way up or output prices go way up, they're not actually adjusting that much. So it kind of suggests that they might not be economic profit maximizers, but rather yield maximizers here. Whereas with soybeans, the price effect seems to be larger. It's still not huge if you think about the fact that soybean seeding rates are very big or large. They're, you know, typical soybean seeding rate is in the 140, 150,000 range. But in any case, the idea of this was to just show that if indeed risk aversion was a major factor, you would think it would go in the same direction, but it goes in the opposite direction. All right, so let me just, I see we're getting we've got about 15 minutes left. I'll just quickly go through a couple of implications. What we wanted to sort of tease out from those estimates we have is this, what does this imply from a magnitude standpoint? Is this really, if farmers are indeed underinvesting in seeding rates, is that mean much in terms of yields, or what, you know, what is sort of the in terms of magnitudes, is that really that significant? And so we did a couple of prediction exercises. What we did was we took that basic baseline model, took the estimated coefficients from it. We plugged in the observed values, so we generate a baseline prediction, and then we did a couple counterfactuals. One is we set the commercial age variable to 0 for all periods, for all varieties. The idea here is if farmers never updated, they never had any new information, what would seeding rates have looked like? And then as a different one, we did, what if from the get-go, they had like the equivalent of 5 years of additional information about that seed variety. Here would be like seed companies or extension, they did pre-testing for the equivalent of 5 years, and so you have all this extra information, and so you better know what the optimal seeding rate is. And then we wanted to see what would this imply for differences in seeding rates compared to, you know, sort of the baseline of the prediction. So here's a simple graph to show what this implies. And so the blue line is just the baseline prediction fitted to the data. The red dots are what is predicted if you have no updating or learning over time, like, and then the green line is if, you know, they were endowed with like the equivalent of more information from the get-go. And so the takeaway from this sort of is that if they have more information, the seeding rate or the planting rate curve would essentially be shifted up, whereas if they got no information, it would be shifted down. And, you know, the equivalent of 5 additional years of information would shift it up by a non-trivial amount, you know, on the order of, you know, say 1,500 seeds per acre. So essentially we would, if farmers all had access to more information, they'd be shifted up on this higher seeding rate curve. And so then the natural question next is, okay, higher seeding rates, but what does that mean, say, for yields? And so then here, you know, ideally what we would observe is we'd have yields in our data. We don't have yields. But in the last 4 years, there's been a couple of papers by a group of researchers. AFRE is the first author on that. And what they did is they have like over 100,000 observations on Pioneer hybrid trial data. And what they use that to do is to estimate empirical yield function as a function of seeding density for different regions in the United States. So what we did here is just to get really a back of the envelope idea of what are these differences in seeding rates imply for yields. We took their estimated empirical yield function based on trial data for a region similar to Iowa and Illinois, the same latitude, longitude. And then we basically plugged in our predicted seeding rates under different counterfactuals, the one without any change, the one with 0 updating, and the one with 5 additional years of information. And then we looked at what does this apply for changes in yields. And so what we found was that, if farmers didn't update at all, if they didn't, do this upward correction, then yields would be shifted down on a shifted down path by about 1 bushel per acre per year, about 0.5% of mean yields in Iowa and Illinois. So it's, 1 bushel is not huge, but it's also not trivial. The total corn acres in Iowa and Illinois is 25 million, so the corn price of $4 per acre. That's about a $100 million change in revenue. And then the other one is that if they had more information from the get-go, say 5 additional years, you predict that, if they were to shift it up on this higher seeding density, then yields would shift up by about, on average, and this could differ depending on the county, say, or where you're located, by an average of about 1 1/3 bushel per acre, about 0.75% mean yields. So it's not huge, but it's also not, this is a reasonable size effect. And one thing to note about this also is that these are gross effects. So this is, a shift up in yield and a shift up in revenue. This isn't taking into account the fact that it does cost you a bit more money to increase your seeding rate. And if you also got to use more, say, nitrogen to apply to those, to the crop, that's also going to cost you a bit more. So that revenue, say, of 100 million change, that's going to be offset by some additional costs associated with that. So to wrap it up, basic idea of this was, we see these interesting, that picture is really what I go back to, and you see that, for a given variety, they're increasing rates over time. What I think we think this is evidence of is that there's been learning about seeding rates over time, and it's occurred with this downward bias, where farmers are starting, at least during the period we consider, and probably historically, is they start too low, and they're always sort of tending to catch up, and it's just sort of a repeating process. And so as a result of this chronic underinvestment, this suggests that, you could, if they had more information, then yields could be shifted up. And from a policy standpoint, one implication of this is that insofar as, learning occurs beyond the individual level, it occurs whether it's from neighbors or from extension and so forth, this suggests it's likely worth it to put some additional resources and money into figuring out a planting rate, so you get closer to the truth quicker. You start closer to the truth, and you get there quicker. And one offshoot of this that I found interesting is that, in the past 5 to 10 years, there's been a growth in databases where now farmers are reporting information about the yields they get from different input rates. And so I wonder if actually that could be, that could aid in getting them, closer to the optimal rate at a quicker speed, if you have these growing databases where they have access to what other farmers are getting from different seeding rates. So, all right, that's it.
Great. Okay, so we will now unmute people. We've got about 8 minutes for questions. So if you have questions, raise your hand and I will let you ask.
Do you want to start with a question from Eric in the chat?
Go for
Eric,
it, dude, while I'm unmuting people.
All right. Eric asks, for corn, were you able to account for fertilizer applied, rainfall level, or irrigation, or other farm level practices that could counteract the water or nutrient demands of a dense stand? Or if there's underinvestment in seed, maybe that's partly because of the cost of applying these additional water/nutrient inputs.
So I could say one thing I did look at and think about was fertilizer prices. and whether, you know, in principle, if you have, say, a decrease in fertilizer price, that would, you know, because a lot of times as you increase your density, you want to use more fertilizer. And so a decrease in fertilizer price, maybe that encourages, but I didn't find any significant trends there. So that it didn't seem to be the case that there were, you know, changes in fertilizer prices or trends that would encourage dramatic differences in seeding rates. Let's see, I'm reading the question here. As far as rainfall level, unless there's a systematic, you know, unless say rainfall is increasing systematically over time, I don't see why that would encourage a systematic trend in seeding rates. And we do, you know, from an empirical econometric standpoint, we include these farmer fixed effects. So that's conditioning on your local weather conditions, at least in an invariant sense. Yeah, and he says as far as there's underinvestment, maybe that's well, it could be that case, but in order for if they start underinvesting and then they increase their investment in seed, it would need to be the case if it were due to the cost of water or nutrient, that the prices of those things are changing over time for them to be the source of that change. If the cost of water or nutrients are not really changing over time, I don't see that as a source of explanation for this, the within variety trends in seeding rates.
All right, let's move to Felicia's question.
Hello, thank you, Ed. I came a little bit late to this talk as we were discussing earlier, so I don't know whether you had already covered this.
Sure.
It seems that there's been constant crop improvement over time through both conventional breeding as well as transgenic methods. And so it might be the case, and I didn't know whether you had already accounted for it, that in the past when farmers were planting relatively lower rates of corn seeds, that might have been the optimal strategy in past years because the corn plants were not bred specifically for resistance to particular plant diseases or climatic conditions.
Yeah.
As corn breeding becomes ever better, it's certainly more possible for the farmers to plant more and more per acre. And the reason that it might be the opposite for soybeans might actually be the fact that corn plants tend to be somewhat vertical in shape, whereas soybean plants are horizontal. There's only a certain amount of leaf, there's only a certain amount of leaf coverage that's optimal for photosynthesis and for the production of soybeans. So it's not really optimal to keep on planting more and more. They'll just crowd each other out because not all of the leaves are going to be overlapping each other. Yeah. And so from a plant physiology standpoint, it seems that might be one of the reasons you see these two different effects.
Yeah, so I'll first speak to so the first part was you said that there's been improvements to corn over time. I completely agree with that. But the one thing about what we did here, for example, with those variety specific regressions to keep in mind is that is for we're looking at the planting rate trends for one single variety. The variety itself has not changed. It's not, it's not like it's becoming better over time. It is the same variety in, say, in the year 2000 as it was in 2005. And what we see is that they're planting that exact same variety at significantly higher rates 5 years later than they were 5 years before. And these variety fixed effects, it also includes the fact that this variety, it could be genetically engineered, it could be not. So I would agree, there may be factors going on that encourage, but it shouldn't be the case that if you look at a particular variety that it's increasing like that. To the second issue with corn and soybeans, I would agree. So there is, you know, one caveat I had in there, but that I didn't discuss, and this is something David's on the paper as well, and he's brought up, is that corn and soybeans do differ in certain ways, in the sense that, you know, soybeans, they respond, you know, they sort of compensate more by in different environments. And so one possibility with this risk aversion aspect is that if seeding rates altered risk in a different way in corn than they do in soybean, it is possible that what can explain these upward trends is still risk aversion. What I would say is that even if it is risk aversion that's driving these upward trends in corn, that's still evidence of learning, because you know, farmers are, even if they're risk averse, the fact that they're going up over time means they're getting more information, they're figuring out that it's a higher rate. And so therefore, from a policy standpoint, it would still be worth it, for example, to invest in acquiring greater information.
Okay, thank you.
Yep.
Song Queen, go ahead.
Oh, yes. So I have a question actually related to some of the earlier question about the timing age. So do you have this time fixed effect in your model, or do you have the planting year of each variety?
No time fixed effects, because then we wouldn't be able to identify that commercial age variable. And you said, what was the second one? You said
so the planting year, right? So you have the age of the variety, but you can also include in when the variety was used or was planted in that particular year, right?
yeah. So that would sort of be, I think that would maybe sort of.
That can control some of the disease and climate. Of course, they are maybe even interact with a region, and have a regional specific this time varying. And the other thing related to that, I was wondering if you look at just the variety released earlier and then later by time, if you, of course, you have fixed effect of variety, but it's still interesting if you just look, in the sense you have a picture showed already over time, the rate is higher. But that if you just by time of variety release, maybe some of the variety, I think that of course related to the channel of learning. So if maybe just extension or the seed companies, they over time they see this corn must be grow more densely, and then they may actually feed back to the farmers, and farmers, of course, that's still part of the learning. But then whether that is it's still interesting to identify the channels.
Yeah, that's so. That is what one thing we have heard from some reviewers from this, and one thing they've wanted us to try and exert some more effort on is the particular channels of learning, whether it is from, you know, whether the learning is occurring at the individual farmer level, or whether it's occurring at the you know, from extension or from the seed company. That's with the data that we have, that's something difficult to do. As to whether, let me see if I can maybe speak a little bit to one of the things you said. So like when I did these variety specific regressions, these varieties are, yes, I've looked a bit at whether, depending on the year that it was introduced, is the rate of increase different. And I didn't find any major significant differences, but like the cow varieties, if I remember correctly, they are introduced a bit later, and their actually rate of increases are larger on average than some of these pioneer varieties. So yeah, there may be some, that's not results that I have off the top of my head, but there may be some differences in the year that it was released as to how fast the increases are occurring.
Yeah, I think you can include the, yeah.
Maiwish?
I realize it's already after 5, so if you think we should.
It's only 4 here.
Let's do one more question.
Okay, sure. So my question was about your last slide, the summary and implications. And, I mean, all of my work is in developing countries, and, I also look at the crop improvement and the benefits farmers get from improved varieties and things. But this is very interesting in the sense, and I'm just trying to understand the implications here. So all these varieties are private sector varieties, which is different than the setting in which I work, where all the varieties are, or most of them are public sector varieties.
Yeah.
So, one can say that it's in the seed company's interest that they should be doing rigorous research in the seeding rate when they release a variety or make it commercially available, because the farmers plant their seed, it's more revenue and profit for them. So in their self-interest, they should be also, they should be doing this, and they should have learned that farmers are under investing in seed and to promote their own seed varieties and sales. They should have already learned that and be doing whatever you are already implying here as additional investment into understanding and communicating optimal rates. So to me, this is a puzzle, and why seed companies have not learned. If farmers have not learned, okay, I understand. But why seed companies have not learned?
Yeah, that's a good question. I guess I would say, well, as a seed company, they probably, they've had probably uncountable many ways they could try to invest their money. It's not just seeding rates to check variations on. They could check variation on nitrogen rates. There's about a uncountable many number of different soil conditions or other types of things that they could possibly test these densities in. So they have to draw the line somewhere. And so, and at the same time too, for each dollar they invest in figuring this out, there's a lot of uncertainty about whether farmers will even adopt this variety. If it's widely adopted, perhaps it would make a monetary sense for them to do. But yeah, it's not clear to me that, I think you could still have it be the case that the companies themselves are behaving rationally by the level of investment that they're putting into seeding rates. But at the same time, there's still an inefficiency there. It's sort of a private social dichotomy that you have there. Whereas, if that were something taken up by a public enterprise, it would be something worth it.
I mean, I know in developing countries, the public sector are inefficient also. So here, basically, these implications, your last bullet, is more directed to public investment rather than private.
Yeah, I would say, yeah. Or extension, extension also has, they have budgets and they have to decide what things they want to put their resources in and what variations they want to look at. And even having said this, it's still possible at the end of the day that there are other variations that would yield more, more information to farmers than seeding rates. I guess I would just say based on this study, it suggests that seeding rates have been too low and that additional, investment potentially towards finding the optimal rate could yield benefits, but maybe they're too low and something else, or maybe they're doing something else wrong and it would yield more money to do that. That's something that I couldn't say.
Sure, and then, this goes back to my first question I had asked is, okay, how do we know that it is the current information and understanding is not correctly communicated to farmers? you said at least you don't have that data, but I'm sure that would be something worth pursuing to back up this implication and recommendation that you're making from your research, to show that there is the current understanding and the way it's communicated to farmers on the optimal rate is suboptimal, and that there is room for improvement.
Yeah, yeah. So is the level of information suboptimal? That's sort of I guess what I think this study shows is that it seems to be the case. You shouldn't have significantly changing input rates, like seeding rates over time, if they're getting things right from the get-go. So that's just, they aren't. But whether or not the information flow associated with that is optimal, I think is, yeah, that's a more difficult question. So in that sense, it's more speculative on my part as to whether that aspect is efficient or not.
And because you're implying public investment in this, it may be, good to at least figure out or have a good understanding of whether it is actually the lack of information, or it's just the way it's communicated, which is not, which is the constraint. And so more, where to put the public investment.
Yeah, I would say this
research or doing.
Yeah, so if I were talking to Extension, I would say this just raises, if you're aware of this or not, this raises the issue of the possibility that, there's been this onward going trend for many, many years of potential underinvestment in seeding rates. Would it be worth it compared to the things that you're currently doing to potentially, do some extra trials of seeding rates? Perhaps there's so many varieties that, maybe they could just make such a small dent that it wouldn't be worth it. But that's sort of the idea of this.
Thank you.
Yep.
All right, let's thank Edward for his great talk, and then we'll conclude the meeting. Thank you so much, Edward. This has been really fun.
Yeah, thanks a lot.
Thank you.